This is going to be a thrilling experience for you. This is the second part of AMGM inequality. And in the first part, we have discussed the proof of AMGM inequality. If you have not watched the part 1, we recommend you to watch it first. In this second part, we shall mainly practice some problems and we shall see that applying AMGM inequality to obtain the required result requires some cleverness, and that makes the problems interesting. Before picking up the problems, let's take a short recap. AMGM inequality states that the arithmetic mean of some non-negative real numbers is greater than or equal to their geometric mean, and the equality holds if and only if all the numbers are equal. This simple inequality, when applying cleverly, makes the problems interesting and challenging. My intention is not just to dump the solutions directly before you, but I want you to come up with the right approach by unfolding the problems layer by layer. This will give you an insight to look why some seemingly relevant approach is not working in particular problem and how we can fix it by bringing some changes in it, and eventually we get the right approach. In AMGM inequality problems, we mainly focus on finding the right numbers on which if we apply the AMGM inequality we get the desired result. Let's see how we do it in the first problem. Let x, y and z be positive numbers and we need to find the least value of this ratio. We are given x, y and z positive. This gives us a clue that the AMGM inequality may be a useful tool here. But it is not immediately clear on which numbers we should apply the AMGM inequality. The obvious three numbers we may bet on are the three terms appearing in the numerator: x into 1 plus y, y into 1 plus z and z into 1 plus x. If we apply AMGM inequality on them, we get the sum of these three numbers is greater than or equal to thrice cube root of x, y, z into 1 plus x into 1 plus y into 1 plus z. And by dividing this inequality by square root of x, y, z, we get this result. But since the RHS is not a constant, so this approach is not giving us the minimum value of the given ratio. So we should apply the AMGM inequality on some other numbers. We simplify the numerator and we get 6 terms. If we apply the AMGM inequality on these 6 numbers, we get x plus y plus z plus xy plus yz plus zx is greater than or equal to 6 square root of xyz. Thus we get the given ratio is greater than or equal to 6, but don't hurry in concluding that the minimum value is 6. We have to show that there exists some x, y and z for which the equality holds. As we know that the equality holds in AMGM inequality if and only if all the numbers are equal. So the equality holds in this inequality when x is equal to y is equal to z is equal to xy is equal to yz is equal to zx. And that gives x, y, z is equal to 1, 1, 1. Now we can safely say that the minimum value of the given ratio is 6, and this completes the solution. In this problem, we learned two important things. One is that the finding minimum and the maximum value is a two-step problem. Set up an inequality, show that the equality can actually hold in the inequality. The other important thing we learned in this problem is that the picking of the right numbers in AMGM inequality requires some thoughtfulness. We cannot apply AMGM inequality on any numbers blindly. Well, let's move to the next problem. Find the minimum value of the sum of real numbers a power negative 5, a power negative 4, 3a power negative 3, 1, a power 8 and a power 10 with positive a. If we apply the AMGM inequality on given 6 numbers, we get the arithmetic mean of these 6 numbers is greater than or equal to 3a power 6 whole power 1 over 6. Again, the RHS is not a constant, so we cannot get the minimum value of the sum of given numbers from this inequality. If we want the geometric mean a constant, then we have to get rid of this extra power 6 of a in the RHS. If we split 3a power negative 3 in 3 equal parts, and reapply the AMGM inequality on resulting 8 numbers, we get the geometric mean constant, and we get the sum of given numbers is greater than or equal to 8, and the equality holds when a is equal to 1. Thus the required minimum value is 8, and this completes the solution. In this problem too, we had to do some work in picking up the right numbers for AMGM inequality. That is why we are telling you repeatedly that despite of a simple statement of AMGM inequality, you require a practice of lot of good problems to master it. Memorizing the mere statement is not enough to tackle the problems. If you want, you can practice AMGM inequality from our book Algebra Volume 2. We have given sufficient number of problems, and to give you an optimum help, we have given hints 1, hints 2 and then solutions. We have written our books by keeping serious students in mind who want everything in detail with logical precision. The links of the books are in the description. Finally, let's move to the third problem. If x, y and z are non-negative numbers with x plus y plus z is equal to 27, find the maximum value of x, y square z cube. I would like to remind you to attempt the problem yourself before watching the solution. If you want, you can pause the video. Believe it or not, if you directly watch the solution without attempting the problem is of no use for you. Let's come to the solution. If we simply apply the AMGM inequality on x, y and z, we get x, y, z less than or equal to 729. But definitely we are not interested in the maximum value of x, y, z. We are interested in finding the maximum value of x, y squared z cube. So we need to hunt for those numbers whose geometric mean contains the term x, y squared z cube. The term x, y squared z cube itself is screaming how to find those numbers. Notice that the exponent of y is 2 and the exponent of z is 3. So it is natural attempt to split y in 2 equal parts and z in 3 equal parts. And then we apply the AMGM inequality on resulting 6 numbers. That gives x, y squared z cube is less than or equal to 3 power 15 over 2 power 4. And the equality holds for x, y, z is equal to 9 over 2, 9, 27 over 2. Hence, the required maximum value is 3 power 15 over 2 power 4. This completes the solution. Hopefully now you are convinced that applying AMGM inequality required some cleverness or creativity to obtain the required result. Cleverness and creativity are two indispensable traits to become good problem solver in mathematics. We have a lot to say about it, and we shall keep saying in subsequent videos. So it is good for you to stay tuned with us. That's it for this video. In the next video, we shall extend AMGM inequality to AMGM-HM inequality. And it is another exciting inequality. You can make sure not to miss such amazing videos by subscribing our channel. Thank you for watching this video. See you next week.